We're now going to get into lifting line theory. This was the first really solid theory that was developed that was capable of predicting the aerodynamics on finite wings. Up to this point, there had been work done on airfoils, and of course, people had made attempts at predicting the lift on a finite wing, but this theory was developed by Ludwig Prandtl in the early 1900s, and it was really the first solid theory that was capable of accurately predicting the aerodynamics on a wing based off of the wing's geometry and operating conditions. And not only did it predict the lift, the total lift, and the what we're going to learn about induced drag, so a portion of the total drag, but it also was capable of predicting the lift distribution along that wing, and where in the spanwise direction that lift was being generated, and how much lift there was, as a function of spanwise location. So we're going to walk through this now, just the basic development of it, and I'm going to take a little bit of a high-level approach, get into some of the math in more detail, but not all of the math in that detail. I'm going to skip some of the larger integrals and things, and just explain what's going on, so that so we can keep a perspective of what we're doing and why we're doing it and how this all fits together. Okay, so let's start off with just a three-dimensional wing here, or a finite wing. And over on the right-hand side, I'm going to keep track a list of assumptions, so we can remember what basic assumptions went into this theory. Okay, and the first assumption is that we're going to say, based off of what we understand, the basic vorticity and how that's distributed on this wing, due to the physics of the flow. The way that Prandtl handled that was that he placed a series of what are called horseshoe vortices along this wing, and so there's one horseshoe vortex that looks kind of like a horseshoe. It's got a bound portion here in the center, and then it's got these trailing portions that go off to infinity. Okay, and that's just a single vortex, and you can place a series of those, and he put them all coalescing here, the bound portions coalescing along what is often called the lifting line. Okay, so we place a series of these vortices, and in fact, we don't even have to have these be horseshoe vortices. We can actually treat this trailing sheet as a continuous sheet of vorticity. Okay, but then the bound portion of the vorticity along the wing all lies along this lifting line here. Okay, so that's called the lifting line. Okay, so now let's put a coordinate system on here. So we've got this sheet aligned with the x-axis, and actually we're going to say that's the direction that the free stream velocity is coming in. Y is normal to that in the upward direction, and then z is actually out the left wing here. Okay, so that's the coordinate system that we're going to use. Let's label y. Okay, and this sheet has a strength. So the strength of this sheet is gamma as a function of z, and we'll put a little t there. That's the trailing vortex sheet strength. That it varies with z. It actually does not vary in x. In the x direction, the sheet does not change strength, only in the z direction. Okay, because of course this horseshoe vortex, one of these vortices, cannot change strength along its length. But in this direction, obviously, we can have a change in strength as we go along the sheet in the z direction. Okay, and then we're going to say that the vorticity here at the lifting line, we're going to call that gamma, capital gamma, and that changes as a function of z. Okay, so this is how we've constructed the problem. So a couple assumptions that have gone into this is that the spanwise vorticity lies on the lifting line. Okay, and then secondly, that the trailing vortex sheet lies on the x-axis, or actually what we more correctly should say in the xz plane. Okay, so a couple things that we are neglecting then by making these assumptions. We actually know that this vorticity, the spanwise vorticity here, it changes with chord location. So really, these should be spaced out in the chordwise direction here to show the distribution of pressure in the chordwise direction. So one thing we're giving up here by placing all of this vorticity along the lifting line here is that we're not going to be able to see how the pressure or the lift is distributed chordwise, but we will be able to see how the lift or pressure is distributed spanwise. Okay, we'll be able to see how it changes in the spanwise direction, but not the chordwise direction. Now, we've placed all of these, all of the trailing vorticity sheet here along the in the xz plane, and by doing that, what we've neglected is the roll up. Remember, we talked about how the fact that this vortex sheet rolls up into a right and left main vortex, and so we're neglecting that. We're saying, you know, this vorticity goes off in a straight line off into infinity, and we're going to neglect the effects of that vortex roll up on either side. Let's write down a few equations here. One thing that we know, because the strength of a vortex cannot change along its length, we know that the strength of gamma as a function of z, the vorticity here, if we were to look at all of the vorticity passing through this point, it's equal to the summation of all of the vorticity on the left-hand side, at least in this example here, that's passing through there. And so the change in gamma with respect to z is equal to the vorticity that's either leaving or entering the lifting line there. Okay, so the change, actually it's the negative of change in capital gamma with respect to z is equal to the strength of the sheet. Okay, so the strength of the sheet is basically telling us how much vorticity is entering or exiting the lifting line up there. Okay, so those two are related, capital gamma and little gamma. Okay, and then using the Biot-Savart law, we can look at the influence of a differential segment. Let's just draw a differential segment over here, and let's see, we'll call that d zeta. So that's we'll call that dl. It's a differential length there. So if we were to integrate, or excuse me, to look at the influence of a differential segment on some other point, and we'll put that point on the lifting line for now. So this is our point of interest here. We would see, using the Biot-Savart law, that the differential velocity that is induced at that point by this differential segment is equal to, let's see, gamma t of z times dz times dl cross r divided by 4 pi r cubed. Okay, so that's just the Biot-Savart law of how much of the induced velocity at any single point. So we can look at the induced velocity from the trailing sheet on points on the lifting line. We can also look at the induced velocity of the lifting line itself on other points along the lifting line. And what we'll find is that the lifting line, or the bound vorticity here, does not induce any velocity along its own length. Okay, so when we're looking at the induced velocity from this whole vortex field here, the bound portion of that velocity does not induce any velocity along the lifting line. And you can prove that. I won't walk through it here, but you can prove that. So what we find is that the induced velocity along this line only results from the induced velocity coming from the shed vorticity. Okay, and so we can integrate all of the influence of this entire vortex sheet. So we'll integrate in x and in z for this whole vortex sheet and look at the induced velocity at every point here along the lifting line. And one thing we'll find is that the induced velocity from that trailing sheet only induces a velocity in the y direction. Okay, so the resulting velocity is actually only in the y direction. It doesn't induce any velocity in the x or z directions. And that induced velocity comes by integrating from negative b halves up to b halves. Now, b halves is simply half of the span up here. So we use span to represent the whole span of the wing there. So we'd integrate from minus b halves to positive b halves, and we would, there's a double integral, we also integrate from x equals 0 off to infinity, and that covers the whole sheet there. And what we would do is add up or integrate this differential velocity that is induced by any xz point back on some point on that lifting line. Okay, and that depends on that's a function of gamma z. So it's actually a double integral where we'd have inside of that integral it's a function of little gamma t of z. Okay, and we can work through that. I won't work through it here, but what we find is that is equal to minus 1 over 4 pi. Now we can do one of those integrals from 0 to infinity. We can perform that integral without knowing this distribution of gamma of z. Okay, the second integral we can't perform without that. But so what we end up with is just a single integral then, after we've performed the first integral. And we'll integrate, and actually we're going to use the variable zeta equals minus b halves up to b halves of, and instead of gamma of z, we're going to replace that with this relationship of d gamma dz. And so what we have there is d gamma d zeta. Actually, we're just going to use zeta as the variable in the z direction. And we're integrating in d zeta, and in the denominator here we have a z minus zeta. Okay, so this is a pretty important equation here. What it's saying is that we can choose any location z along the lifting line, and of course x and y are both 0 there. We've placed the coordinate system along the lifting line. We can figure out the velocity in the y direction at any z location by running this integral here, and it depends on that location z minus zeta. We use zeta to integrate as our variable of integration from negative b halves to b halves. Okay, so this tells us the velocity in the y direction due to that integral. Okay, let's now that we know that velocity is only in the y direction, we can step back and look at what's happening locally to the airfoil at any location. So let's draw the cross section here of an airfoil in this setup here. So this lifting line, the whole development, we've placed this trailing vortex sheet in the xz plane. Okay, so that's this line here is the xz plane, And but the airfoil doesn't have to be aligned with that. The airfoil can be set up, you know, at some angle to that. And there's the lifting line there right along the z-axis. And but we did say that the the xz plane was aligned with the free stream velocity v infinity. Okay, so what we get here is let's draw in the chord line. So that's the chord line. And this angle here is what we would call alpha. Alpha is the angle of attack between the chord line and the free stream velocity. Well, we know that we have some induced velocity, v sub y, and I'm going to call that v sub I. That's the induced velocity. It's only in the y direction. Remember, from the vortex sheet, we get some induced velocity in the y direction. And so what's going to happen is my actual velocity that this airfoil sees is the summation of the free stream velocity plus this induced velocity, which is in the downward direction a little bit. And so it's going to change the incoming velocity vector here slightly. And so that will be rotated, so that free stream velocity, or the velocity that the airfoil actually sees, will be rotated by what we'll call the induced angle of attack, alpha I. And if you take alpha minus alpha I, then we have alpha effective. So this is the effective angle of attack. Okay, so that's the angle of attack that airfoil is actually going to experience. It's the summation of v infinity and the induced angle of attack. So let's write out what that would be. So alpha I, the induced angle of attack, we can use small angle approximation and say that is approximately negative Vy over V infinity. Okay, it's the ratio of Vy to V infinity. That's the small angle approximation. So let's add that actually to our assumptions here. We're going to say that alpha I is small. That's another assumption or approximation we're making here. Okay, so we have an equation for v sub y, so let's just plug that in here to this alpha sub I. And what we'll get here, we've got a negative out front, so those will cancel, and so we'll have 1 over 4 pi v infinity times the integral of zeta equals negative b halves to b halves of d gamma d zeta over z minus zeta. Okay, and remember that this d gamma d zeta here is related to gamma, the gamma of z or zeta, the strength of that vortex sheet. Okay, so that's our equation for an induced angle of attack. And now from airfoil theory, let's draw back on what we understand from airfoil theory. We know that the lift coefficient from airfoil theory at any z location, we can write that as CL alpha, the two-dimensional lift slope, times alpha effective, our effective angle, which can be a function of z, minus the zero lift angle of attack, which can also be a function of z. Now, that zero lift angle of attack would be a function of z if the airfoil changed camber, for example, as it moved from the root to the tip or something. We're just going to leave it as a function of z. It doesn't complicate things very much. And we know that alpha effective is the difference between our global angle of attack alpha minus the induced angle of attack at any location z. Okay, so remember we had this global angle of attack here. We minused off the induced angle of attack, and that gave us the effective angle of attack that airfoil section is seeing. So we can plug that into our lift coefficient equation. So CL of z is equal to CL alpha times, I'm going to say alpha minus alpha I at z, minus alpha L0 at z. Okay, so those can be functions of z. Okay, so one more thing that we want to pull in here in order to close this formulation is the relationship to the Kutta-Joukowski law. So that lift coefficient can actually be written a different way. That's simply the non-dimensional lift, which is 1/2 rho v infinity squared c. So that's the two-dimensional lift coefficient. And we can use the Kutta-Joukowski law to relate that lift. It's actually rho v infinity times gamma, the strength of the vorticity, over, again, 1/2 rho v squared infinity c. And the rho's here will cancel, one of the v infinities will cancel, and so we're left with 2 gamma, which can be a function of z, divided by v infinity, which can, v infinity times c, which can also be a function of z. So the chord distribution and gamma can be a function of z. And of course, that's what we've assumed here from the beginning here, that gamma is a function of z, that it's going to change as we move across that wing. Okay, so let's pull these things together now and rearrange this. So let's set, I'm just going to rewrite and set this equal to that right there. So we're going to get 2 gamma of z divided by v infinity c of z is equal to CL alpha times alpha minus alpha I at z minus alpha L0 at z. Okay, and the final step here is to plug in our equation for alpha I here. This is our integral equation for the induced angle of attack. We're going to plug that right in here for that alpha I, and then we're going to rearrange just a little bit and move that term to the left-hand side. And so what we'll get is 2 gamma of z over v infinity c of z plus CL alpha, that alpha I is multiplied by CL alpha, over 4 pi v infinity times the integral of zeta equals minus b halves to b halves of d gamma d zeta over z minus zeta, and that is equal to CL alpha minus alpha L0 of z. Okay, this is the fundamental equation of lifting line theory. This is what Prandtl developed. The nice thing about this is that the only unknown in this whole equation is a gamma as a function of z. That's the only, let's see, that is the only unknown. Okay, so we can use this equation now to solve for this distribution, and that shows up in 2 places. We've got gamma of z right there, and then we've got the derivative of gamma with respect to zeta, where zeta is related to z. It's in the z direction. So anyway, these are the 2 places that it shows up, and this is called an integral differential equation, and we're going to learn a way to solve this type of equation using an infinite series. But this equation, basically what it says is that the lift that is occurring at any location along this wing. So if we look at the lift at the spanwise location here, that lift has to the lift that we would get by including the induced angle of attack from all of the downwash or the vorticity, this vortex sheet. If we include all of that downwash, and that's this induced velocity here, if we look at all of that and add it up there, and then take that and change the angle of attack by that amount, that alpha I, what we're left with is an effective angle of attack, and And that effective angle of attack is related to the lift coefficient over here from two-dimensional airfoil theory. So that lift has to be able, the lift that we predicted from two-dimensional airfoil theory at that effective angle of attack has to be equal to the lift that we would get from the Kutta-Joukowski law, which we could get from the strength of gamma at that location. So we had two pieces of information that we knew: gamma, the strength of gamma, or at least we had an equation for that, of how it's related to the downwash here. We also had an equation for how the lift would be affected through this induced angle of attack at that location. And so we set those two equal, and that's the crux of the problem right here, is that we equate these two definitions of lift at that location, and we know that the induced angle of attack can be written in terms of this downwash, or excuse me, the integral of the vorticity, the vortex sheet, and by equating that, we come up with this equation that only has one unknown, which is the distribution of gamma. So this is the fundamental lifting line equation, and these are the assumptions that go into it here: that the spanwise vorticity lies on the lifting line, that the trailing vortex sheet lies in the xz plane, and that the induced angle of attack is small. And once you do that, you can develop this equation, and in the following videos we're going to learn what we can do with this equation, how to solve it, and get forces and moments out of this.